All right, let's talk about something you probably use every single day. A spoon. Seems simple, right? Well, it turns out there's some seriously cool physics hidden right there in its surface. We're talking about curved mirrors and how they completely shape the world you see.
Come on, you know you've done this. You pick up a spoon, maybe at the breakfast table, and bam, your face is upside down and all distorted. Then you flip it over, and it's totally different. So what's going on there? It's not magic. It's not just some weird funhouse trick. It's actually some really fundamental laws of light in action.
So get this. That single spoon is basically two different kinds of scientific mirrors. The side you eat with, the one that's curved inward, that's what we call a concave mirror. And the back, the part that bulges out, that's a convex mirror. Two completely different optical instruments in one simple object.
So how are we going to break this all down? Well, first, we've got to start with the absolute basics, the one simple rule that light always follows. Then, we'll get into the anatomy of a curved mirror, learn the lingo. After that, we'll solve the mystery of that upside-down image. And finally, we'll see how this whole spoon thing connects to some really amazing real-world tech.
Okay, first things first. Before we can even talk about curves, we have to talk about straight lines. Because it turns out there's one super simple fundamental law that explains how light bounces off of any surface. And here it is. It's actually incredibly simple. The angle that light hits something is the exact same angle it bounces off at. That's it. This one little rule is the key to everything else we're going to talk about, whether the mirror is flat or curved like our spoon.
All right, now let's get into the specifics. To really understand what's going on, we kind of need to learn the language, the key landmarks on the map of a curved mirror. Don't worry, it's pretty straightforward.
First up, we have the pole. Scientists usually label it with the P. Honestly, just think of it as the dead center of the mirror's surface. It's like the starting point for everything.
Okay, next we've got the center of curvature, or C. Here's a good way to think about it. Imagine your mirror is just a little slice cut from a giant hollow glass ball. The center of curvature is the exact center of that original big ball. So for the inside of our spoon, this point isn't even on the mirror itself. It's just kind of floating in space out in front of it.
Now, this next one, the principal focus, or F. This is where things get really cool. This is where the magic happens. Imagine a bunch of parallel light rays, like from the sun, hitting the inside of the spoon. They don't just bounce off randomly. They all get focused down to one single point. And this is a real thing. You can literally concentrate so much energy at this one spot that you could burn a hole in a piece of paper. Pretty wild, right?
And that leads us to the focal length. It's just the distance from the center of the mirror, the pole, to that powerful focal point we just talked about. But it's a super important measurement. Why? Because it tells you how powerful the mirror's curve is. The shorter the focal length, the more curved the mirror is, and the more power it has to bend light.
Okay, so we've got the lingo down. We know the key players, the pole, the center of curvature, the focus. Now let's put it all together. Let's see how these things actually work to create that weird upside-down reflection we see in a spoon.
Here's the really crucial thing to get. With a regular flat mirror, your reflection is always predictable, right? It's just you. But a concave mirror is totally different. The image you see completely changes depending on how close or far away you are. It can change size, it can flip upside down. It's a total reality bender.
So how can we possibly predict what's going to happen? Well, physicists have a clever trick called ray tracing. It sounds complicated, but it's not. They just follow a few very simple, predictable paths that light rays always take. You can see the rules here, and wherever those reflected rays cross paths, bam! That's where the image appears. It's like drawing a map for light.
And check this out. This is what all that ray tracing predicts. It's the whole secret of the spoon, right here. When you're far away from it, your reflection is small and, yep, upside down. But watch what happens when you get really close, closer than that special focal point. Everything flips. Suddenly, your reflection is right side up, and it's huge. That's exactly how a makeup mirror or a shaving mirror works. It's not a different kind of mirror, you're just standing in the right spot.
Okay, so this is all fun to know about your breakfast spoon, but why does it actually matter? Well, because these exact same principles are behind some incredibly powerful and important technology that we use all the time.
Think about it. That ability to focus light into one point, that's what's inside your flashlight and your car's headlights, creating that powerful beam. That magnifying power when you get up close, that's what your dentist is using to get a supersized view of your teeth. And that thing about burning paper? Yeah, on a massive scale, that's how solar furnaces work. concentrating sunlight to create incredible heat.
But hold on, what about the other side of the spoon, the back? Well, that's the convex mirror, and its story is way simpler. It always does the same thing. It makes a smaller, upright version of you. It also gives you a much wider view of everything behind you. You know those big round mirrors in the corner of a convenience store? That's a convex mirror. Same exact principle as the back of your spoon.
So you see, it all boils down to this one simple idea. A reflecting surface can be curved inwards or outwards. From that one tiny difference, this whole world of optics opens up, shaping everything from giant telescopes to the mirror your dentist uses.
So what's the big takeaway here? It's that the same exact physics that runs powerful solar furnaces and massive telescopes is literally hiding in your kitchen drawer. That simple curve in a spoon bends reality in ways that are both predictable and incredibly powerful. So now that you know the rules of the game, what other everyday things are you going to look at a little differently?